just to go over a few standardized things. When we're talking about angles on a coordinate grid, we're going to always have them in standard position, which means the initial side is along the positive x-axis, and the terminal side, or the ending of the angle, is measured in a counterclockwise direction. So we're always going to be measuring angles like this. So from the positive x-axis around or up to the terminal end. Some things that are not standard, so we won't be doing, so please don't ever draw your graphs like this, is having a initial side not on the x-axis and then the terminal angle somewhere else. This is still technically an angle, but that is not in the standard position that we will be using. We will always start from the positive x-axis. We will also always start having the vertex of that angle at the origin. So though this starts on the x-axis, it's not at the origin. That is not standard position. So all of the graphs, all of the lines that we will be doing, all of the angles will be from the standard position always for like the next forever. So when we put it on a graph, that's what we're talking about with standard position. This is also going to sound hopefully a little bit familiar for you. The angles in a triangle, there are a bunch of trig measurements that have to do with the relationship between different sides of a triangle. The acronym that you would have used to learn this, hopefully, is SOHCAHTOA. Does that sound familiar at all? Yeah, okay. So SOHCAHTOA means that sine is the opposite over the hypotenuse. Cosine is the adjacent side over the hypotenuse. And tangent is the opposite over the adjacent. SOHCAHTOA. SOHCAHTOA. The way that this works is that for all of these trig measurements, for sine, cosine, and tangent, they have to do with the related sides to your angle theta. The angle, or the side directly across from theta, is your opposite side, because it's opposite of the angle theta. The side that is touching theta, that is not your hypotenuse, is your adjacent side. And obviously your hypotenuse is the longest part of a right triangle, so here is your hypotenuse. So if we know a theta, we're going to be able to find all of the sides for opposite, adjacent, and hypotenuse. So to write this out in formulas, sine is the opposite side over the hypotenuse. So you would write a ratio, whatever the length of the opposite side is over whatever the length of the hypotenuse is. Cosine would be the adjacent over the hypotenuse. Tangent would be the opposite over the adjacent. And that is the three basic trig functions. But we have actually three more. We have sine, cosine, and tangent, yes, but we also have cosecant, secant, and cotangent. We're going to give them two definitions each because there's two very useful definitions for each of these. Cosecant is written below below sine, because it is actually 1 over sine of theta. So it is the inverse. It is the reciprocal, inverse was the wrong word, it is the reciprocal of sine, which means if we were going to write it in terms of the triangle, it would actually be the hypotenuse over the opposite side, because it's just the reciprocal of the sine function, of the sine ratio. Secant is defined to be 1 over cosine of theta, so it is the reciprocal of cosine, which means that in terms of this triangle, it would be the hypotenuse over the adjacent. And cotangent, really easy to remember, is the reciprocal of tangent. So cotangent, tangent makes sense, which means that this one is the adjacent side over the opposite side. So if you know 3 trig functions, you actually know 6 of them because you just reciprocal the number. and you have the other trig functions, the definitions of them. This is one of the things I'm going to have you memorize. But luckily, if you just remember SOHCAHTOA, that's the whole thing. Because if you can remember SOHCAHTOA, then you just flip everything over. Those are the other three. Cool. Why would we use this, or how would we use this, is write in example 1. Using the triangle on the right, we want to find all 6 trig functions of the angle theta. So before we get started doing all the 6 trig functions, we need to make sure we know a value for the opposite, the adjacent, and the hypotenuse. Which 2 sides do I currently know? Adjacent and hypotenuse, which means I need to find the opposite. So we dig back through our memories of right triangle geometry. What's like the theorem everybody is obsessed over that you can use with a right triangle? Pythagorean's theorem, a squared plus b squared is equal to c squared. That is for right triangles. And today we will be using right triangles, but eventually we will be doing other things. But right now we can use Pythagorean theorem. And Pythagorean tells me that the opposite side is going to be equal to the square root of the hypotenuse squared minus the adjacent side squared. I'm solving a squared plus b squared equals to c squared in a usable format. Because I would technically be finding like b squared. So you subtract a squared to the other side, take the square root, and we'd be able to find the opposite. Well, that's something I can throw in a calculator. The square root of 29 squared minus 21 squared. I see some people typing. What's it equal to? 20. If we get a radical number or a decimal, you'd have to leave it in radical form. But since we got a nice pretty number 20, we can write it as 20. Cool. That means the opposite side is 20. With that information, we can do all 6 trig functions. Sine of theta is simply equal to the opposite over the hypotenuse. What number or what length is opposite of theta? 20, and the hypotenuse is 29. So sine of theta is 20 over 29. Cosine of theta would be what? Adjacent, so yeah, 21 over 29, because that's the adjacent over the hypotenuse. And tangent of theta? 21. Fabulous. Just as a quick note, because I don't think I said this when I was introducing the trig functions, it is one of my biggest pet peeves to hear somebody call sine sin. It is not sin theta. Do not say that. That feels like nails on a chalkboard for me. It is sine. It is not cos theta. No, cosine. Say it correctly. Sine, cosine, and tangent. Okay? But once we have these 3, sine, cosine, and tangent, finding cosecant, secant, and cotangent is very easy as long as you remember which trig function they're related to. Sine and cosecant go together, which means that cosecant of theta is just 29 over 20, the reciprocal of sine. Secant of theta would be 29 over 21, the reciprocal of cosine. And cotangent would be 21 over 20, the reciprocal of tangent. A lot of them, yes, because a lot of times with these kinds of questions, I'm going to ask you for all 6 trig functions, which means if you find 3, you just reciprocal them to find the other ones. Any questions so far? Okay, we're still on the next question, finding all 6 trig functions, but I've given you a different piece of information on the back. This time I didn't give you a triangle picture. I gave you one of the 6 answers. And surprisingly, that is enough to find all 6. Because if I tell you that sine of theta is 5 over 6, which 2 sides of this triangle did I tell you? The opposite and the hypotenuse. Great. Let's label that just because that way we remember. This is the opposite. This is the hypotenuse, which means the only other thing I need is the adjacent side. I find it helpful to still see all of this in a triangle, so I'm going to go ahead and draw one for myself, making sure it's a right triangle, and label one of the angles theta so you know which side you're using. What should I label this side? 5. And the hypotenuse is 6. So how do I find that missing side? Pythagorean theorem. I'll take my time this time since I confused you, I think, when I did it the first time. Pythagorean theorem says a squared plus b squared equal to c squared. Which of those two letters do I know? A and C, sure. So if we fill that in, this is a squared plus b squared equal to c squared. If I'm solving for b, I would subtract 5 squared to the other side. And then do what to get b by itself? Square root. I jumped on the last problem straight to this point, which if you know you have one side and a hypotenuse, you can just do this. I don't need to see you deriving Pythagorean theorem, but if you don't know which ones you're doing, you don't know if you add or subtract, just go ahead and use Pythagorean theorem. This time when you do it, if you were to do the square root of 6 squared minus 5 squared, you're going to get a really ugly decimal. So we need to go back and put it in radical form. So instead of starting with the square root, in your calculator, you just do 6 squared minus 5 squared, which is 11. So our side that we're missing is going to be square root of 11. That's my adjacent side. Yeah, don't make it a decimal. I want exact answers, which means you leave things in radical form. Maybe simplified radical form, but radical form nonetheless. Okay, now we can do all 6 trig functions. Pretty obvious. We know sine, because they gave it to us, 5 over 6. Woo! Cosine of theta. Ooh, I wrote an 8. What in the world? Cosine of theta would be what? Remember cosine, SOHCAHTOA.
5 over square root of 11.
Okay, SOHCAHTOA. So adjacent, hypotenuse. What's the adjacent side? Square root of 11. What's the hypotenuse? 6. SOHCAHTOA. I just wrote TOA. So tangent is going to be the opposite over the adjacent, which would be 5 over square root of 11. Now, there is some debate between textbooks, the internet, and mathematicians as to whether you can leave your answer like this. I don't like the answer being left like this, and I don't think your textbook leaves your answers like this, because you're not technically allowed to have square roots in your denominators. So I don't think I've ever talked about it in this class, but does anybody know how you would get rid of a square root from a denominator? Multiply it by its same square root. So you're multiplying by a scalar. I'm multiplying by 1. Square root of 11 over square root of 11 is 1. I'm allowed to do this. And what happens is the square roots are going to cancel each other out. The denominator just becomes 11. And the numerator is 5 square root of 11. That's called rationalizing the denominator. I will ask that you rationalize denominators when necessary. And I believe your textbook does the same thing. Okay? Cool. Whew. But we've got 3, which means doing the other 3 really easy. What is partnered with sine?
Or if you put the opposite of the inverse of tangent of theta, wouldn't you still have a square root in the bottom? I mean, yeah.
When you're doing cotangent?
Yeah.
I would go back to doing this one and flip that, because then it's not in the bottom.
Also, you don't have to do that on bottom.
Well, you can. Technically, if you flip this, it ends up being back. When you rationalize the denominator again, it becomes what we had. I'll show you when we get there. What's the opposite of sine? Okay, what is CSE called? Cosecant. Cosecant. Say that to yourself. Cosecant. We're going to pronounce things correctly. Cosecant of theta is just the flipped version of sine. 6 over 5. Ooh, done. What's the opposite or the related one to cosine? Ooh, how do we say that? Secant. Secant is just going to be 6 over square root of 11. But hopefully your spidey senses are tingling because we just put a square root in the denominator.
6 square root 11 and 11.
6 square root of 11 over 11. Rationalize the denominator. The inverse of tangent is cotangent. That one's easy to remember. And like I was kind of saying earlier, I wouldn't try to flip the 5 square root of 11 over 11, because then you'd still have a square root in the denominator that eventually would reduce out. I would go ahead and use this one, 5 over square root of 11, and flip it, because then you just have square root of 11 over 5, and you don't have to rationalize a denominator. But if you did, and you did it correctly, you'd end back up with this answer. So all 6 trig functions we can find when we're given one trig function, which is cool. Feels like you got no information at all, but really you got a lot of information. Okay. Okay. We got 2 famous triangles. Have y'all seen these triangles before? A 45, 45, 90 triangle and a 30, 60, 90 triangle. These triangles are your best friends. These are the ones that you're going to hear about the most for the next 9 weeks, because a lot of our trig functions are going to be done at these angles. And so this table of values is the next thing I'm going to have you memorize, because we are going to need to be like this quick in doing all of the trig functions for these 3 angles. What I mean by that is, and we'll fill out the table first, and then I'll show you how to get the answers, but then I want you to memorize them so they're quick facts and you don't have to figure them out. If we have 30 degrees, first of all, what is 30 degrees in radians? Oh, we forgot. So 30, to make it radians, we're going to add a pi to it, so it would be 30 times pi over 180. The zeros cancel out, and what's 3 divided by 18? 6. So 30 degrees is the same as pi over 6. That's the first thing you're memorizing. 30 degrees is pi over 6. 45 degrees, if we were doing that one, and I'll show the work for it, but then I'm going to erase it. 45 times pi over 180. No zeros cancel out, but what do 45 and 180 have in common?
5.
Okay, we can do that. So this would be 9, and this would be 36. What do 9 and 36 have in common? 9. 9 divided by 9 is 1. 36 divided by 9 is 4. So 45 degrees is actually pi over 4. That's the second thing you're memorizing. On your own, find me 60 degrees in radians, please. See if we remember. What'd you get? Very good. Okay, cool. That's the third thing you're memorizing. And let me tell you how to very easily memorize this. This is my brain works this way. 45 gets 4 because there's a 4 in it. 3, 6, 3, 6, but they can't be matched up. So 60 degrees does not get the 6 in the denominator, gets the 3. 30 degrees does not get the 6 in the denominator, or 3 in the denominator, gets the 6. So those are opposites. So same number, opposite numbers. That's how my brain memorizes it. But also 180 divided by 3 is 6. 180 divided by 6 is 3. Multiple ways you can memorize it. Those 3 things we have to have memorized. Okay. The other things we're going to have memorized very quickly in this class is all of the sine, cosine, and tangent functions for these 3 angles. We're going to find them the first time, and then we're just going to have them memorized next class. If we were finding sine of 30, remember sine of 30 means I want the opposite over the hypotenuse. So what is sine of 30? 1 over 2, 1/2. Great. We're memorizing that. If I wanted sine of 45, remember that is 1 over the hypotenuse, which in this case is square root of 2. 1 over square root of 2, but then we have to rationalize the denominator like you're doing. If it's 1 over square root of 2, and then we're going to let that 1 in the front be invisible because that's too much. So it's just going to be square root of 2 over 2. You weren't wrong, it's just not perfect. Okay. And then we're going to do 60 degrees. So again, with 60 degrees, I want the opposite of 60 degrees and the hypotenuse. So square root of 3 over 2. Do you see a pattern in the sine of theta row? They're all divided by 2. Great. What else? They kind of just go 1, 2, 3. And technically, they really go 1, 2, 3, because what's the square root of 1? So they really are 1, 2, 3. You're taking the square root of the top. 1, it just comes out. That's pretty cool. That's a nice little pattern to help us memorize this. After lunch, we'll fill out the rest of this table. Okay, so we filled out the sine row. We noticed the pattern that they're all divided by 2, and it kind of goes 1, 2, 3. Great. Let's do cosine. So when we do cosine of 30, cosine is adjacent and hypotenuse. So we want this number over this number. So cosine of 30 would be square root of 3 over 2. Check. Cosine of 45 would be adjacent over hypotenuse, which was 1 over square root of 2. But if we rationalize it, what will that be?
Square root of 2 over 2.
Square root of 2 over 2. You can kind of see the pattern occurring here. Yep. If we do the cosine of 60, the adjacent side to 60 is 1, and the hypotenuse is 2. So it would be 1 over 2. Check out that pattern. All still divided by 2, this time going 3, 2, 1. Easy pattern to help us memorize it. Now we go to tangent. If we want to do the tangent of 30, tangent is opposite over adjacent. So it would be square root of 3 over 1, which is just square root of 3. Let's see. Tangent of 45 would be the opposite over the adjacent, which is 1 over 1. Just 1. And last but not least, tangent of 60 would be the adjacent side over the opposite side. It would be 1 over square root of 3. But when we rationalize that denominator, it'll be square root of 3 over 3. Yes?
For cosine, 45 degrees,
Yes.
where did we get the 2 for the bottom of the fraction?
That's a great question. So when we were doing cosine of 45, it was adjacent over hypotenuse. So it would be 1 over square root of 2. But we have to rationalize that denominator, so we multiply by square root of 2. So it would be square root of 2 over 2. Yeah, that's a good question. Okay, cool. So this table right here is something I need you to memorize. 1000%, it will get a lot easier this class when you have this memorized. In fact, for the next foreseeable future to enter the classroom, you will have to answer one of these questions. They're that quick math facts. But to help you out, there's actually another trick besides the patterns that we've kind of identified to help you know these different things. I want you to flip to the very last page. It's called the hand trick. Okay, the very last page of your notes.
What's the nice trick?
Okay, go back for a second to this. We wrote it down backwards.
I thought I had it right the first time. I was like, what?
Y'all gotta tell me when I'm doing something silly. This should be square root of 3 over 3, and this one should be square root of 3.
When I had started
So my
doing it, I
answer
was
to
like,
you was right. Square root of 2 over 3. No, I said 2.
You said 2, but yeah. So sorry. There's my human moment for today. We're all allowed some. But now the pattern makes sense. I was like, I know I've used this piece of paper last year and it was fine. On this last page of your notes, it has a trick for you to remember all of the sine, cosine, and tangent functions for 45, 30, and 60 degrees in quadrant 1. Your left hand, sorry, yeah, this is my left hand. What? Your left hand is quadrant 1. This is the x-axis, this is the y-axis. So pinky is your x-axis, your thumb is the y-axis. The first angle, going from smallest to greatest, would be 30. The second angle would be 45, and then you would have 60 degrees. So if I said show me 30, you would do this with your hand. So everybody do this with your hand. This is 30 degrees. If I say show me 45, what would you do? And then show me 60. Okay, The reason that this is important is because there's a pattern with your hand and the number of fingers that are showing for each sine function, cosine function, and tangent function. If I wanted to find the sine of 30, I'd put down the 30 finger, which is the ring finger. For sine, you want to take the square root of the number of fingers below the 30 finger. How many fingers are below your 30 finger?
1.
What's the square root of 1? Divided by 2. Sine of 30 is 1/2. 1 divided by 2. Okay, the sine of 45, how many fingers are underneath here? Square root of 2 over 2 is the sine of 45. Because there's 2. All of them are divided by 2. Look at the formulas here. It says number of fingers below divide by 2. Yes?
You don't actually divide them, you just put them.
Just put them. Yeah, divide it by 2 because it's not divisible by 2. And if we were doing sine of 60, 60 is your index finger. How many fingers are below? So square root of 3 over 2 is the sine of 60. Okay, if we do cosine, cosine of 30, again, this is the 30 finger. For cosine, it's the fingers above. How many fingers are above my 30 finger?
3.
Square root of 3 over 2 is the cosine of 30. Square root of 2 over 2, so there's 2 fingers. Square root of 1, which is 1, over 2, 1/2. Tangent is just the combination of the two without the number 2 in it. So you want the number of fingers below on top and the number of fingers above on bottom. So if I was trying to find the tangent of 30, how many fingers are below? 1. How many fingers are above? That feels backwards. Hold on. Okay, so this works. This is an easy way to help you memorize them so you're not just straight up memorizing facts. So when I ask you the questions at the door next time, because seriously for the next 3 weeks, every time you enter the classroom you will be asked a question. If you need to look at your hand and do this, that's fine. In fact, I encourage it. Okay, because you always bring your hands with you so you can figure out the tangent, cotangent. So sorry, sine, cosine, and tangent. Okay, that's the hand trick. This will become very helpful too when we start going outside of quadrant 1, which will happen in the next few class periods. But right now we're staying within quadrant 1, which is just your left hand for these. So one more time just to review. Show me 45. What does 45 look like? What does 60 look like? What does 30 look like? Cool. We got it. All right, great. So we go to these practice problems. Again, these kind of turn into just quick facts as long as we remember what it's asking for. You can use your hand trick to remember it. Try not to just flip back to the table because we're going to try to use the table and memorize the table. So if we were finding sine of 30 on your hand, which finger would you put down? Ring finger. Sine is below. So how many fingers below? 1. Square root of 1 is 1. We divide that by 2. So sine of 30 is 1/2. If we do sine of pi over 3, first of all, we need to remember what angle measurement pi over 3 is.
Square root of 3 over 3.
Well, what angle measurement is pi over 3? 60. So which finger is that?
Pointer.
Your pointer finger. So how many fingers below?
3.
And then we divide it by 2. So sine of pi over 3 is square root of 3 over 2. Because sine of pi over 3 is just like sine of 60 degrees. Cosine of 45. Which finger do you put down for 45? Middle finger. And cosine is above. How many fingers above? 2. So it's square root of 2 over 2. Tangent of pi over 4.
Square root of 2 over square root of 2.
Yeah, so pi over 4 is what degree measurement?
45.
45 degrees. So again, we're doing tangent of pi over 4. Tangent is below divided by above, which is square root of 2 over square root of 2. That's 1. And now I ask you about cosecant.
Oh, 2 or 1.
Let's see. Okay, cosecant of 45 degrees. Cosecant is related to which trig function?
Cosine. I mean, sine.
Sine. So if we found sine of 45, which is something we can do very easily on our hand, sine of 45 would be the number of fingers below, square rooted, divided by 2. But that's sine. What is cosecant? The reciprocal of that. So say it again.
2
And would I leave my answer looking like that? No, so what would you do?
Multiply it.
Multiply it by square root of 2. And then what happens?
Then you get rid of the 2.
Then the 2's cancel, and so yeah, you just have square root of 2 for this one. That's a weird one where that happens. Not all the time will you have to do the extra step of it canceling, but in this case, we did. Whew, okay, more trig. Secant of pi over 6. First of all, pi over 6 is what?
Oh, 30.
30 degrees. And secant is related to which trig function? Cosine of 30 degrees. Okay, cosine 30 degrees. Which finger is 30 degrees? Ring finger. Cosine is above. How many fingers above?
3.
So that cosine of 30 would be square root of 3 over 2. But we want to flip it for secant. So we use the reciprocal, but we don't leave our answers looking like that. We rationalize. And that time we didn't have to reduce anything because the 2 and 3 don't cancel. Can I give you the last 2 to try?
Yeah.
If you need to flip back to the other table, that's fine. But try it. You got it. Okay, how'd you do?
Terrible.
Uh-oh. This is tough because it's like such little things. I just have to like keep figuring out which one's right. But if I was talking through this one for myself, for cotangent of 60, I know cotangent is related to tangent, so I'm going to find tangent of 60. Put my 60 finger down. The number of fingers below is 3, and the number of fingers above is 1. You take the square root of both of those, if possible, which you can take the square root of 1. So to put it back in cotangent, you just use the reciprocal. And then you have to rationalize the denominator. For cosecant, cosecant is related to sine, and the sine of pi over 3 is like the sine of 60 degrees. So sine of 60 means I put my index finger down, and I just want the number of fingers below divided by 2, so this is square root of 3 divided by 2. But to make that cosecant, I'm going to use the reciprocal and have to rationalize the denominator. Cool, great. Tough, but they're just trig facts. We'll get better at it as we keep doing them. But luckily, whenever you're in a pinch and don't actually know what to do and have a calculator at your disposal, which you will for some parts of class, you can evaluate these in the calculator. You have to be sure, though, that you're in the correct mode. Your calculator thinks in both radians and degrees. Right now, click on the word mode. Your calculator is probably in radians. It's like the third option can change between radian and degree, correct? So when we are trying to do the first problem, which is sine of 63 degrees, you have to go change your calculator to degree mode before you press it, otherwise you will get the wrong answer. Once it's in degree, you can quit that screen, and you have sine, cosine, and tangent just right above the comma and parentheses on your calculators. So literally all we would press is sine of 63 and press enter, and your calculator tells you that it is approximately 0.891. If you had left your calculator in radians, you would get a completely different answer. Now that's too easy though. So the other kinds of questions you might see when I'm asking you to evaluate the calculator is maybe I've given you the measurement in degrees, minutes, seconds. How did we convert degrees, minutes, seconds to degrees?
The number over 60 to minutes.
Yeah, we plus the number over 60 to minutes, so we would do 54 plus 12 divided by 60 to get it back in degrees. And that would be 54.2. Now that's the degree measurement I can type in my calculator. But again, too easy. Do you see a secant button anywhere? No. But what is the relationship between secant and something showing on your calculator? Cosine. So what we can do is we can take the reciprocal of cosine of 54.2. That's telling your calculator to flip it over, and it's going to give us secant of 54 degrees, 12 minutes. So we would do, I'm going to do the fancy fraction because I like it, 1 over cosine of 54.2 degrees. You press enter, and you get approximately 1.710 if you round to 3 decimals. So way too easy because you can just type them in. What makes it more challenging and the kinds of questions we would put in the calculator is the ones where you have degrees, minutes, seconds. Can you guys try letter C?
Yeah.
So you're giving it in degrees, minutes, seconds. I need it back in degrees. And then remember the relationship. And I'm going to stop talking. Awesome. Okay, cool. So if we look at the next question here, part D. What angular measure are we measuring in for part D? Are we measuring in degrees? You could, because pi over 3 is how many degrees? 60. So you could type tangent of 60 in your calculator. But if you don't feel like doing that, or maybe it's some radian measure you don't know the quick conversion for, just change your calculator back into radian mode. So we go back to mode, go down to radians, quit, and then we can type it in. Tangent of, use the pi button, pi divided by 3, and it will give you approximately 1.732. Now what's cool about this is we also just did tangent of 60. Tangent of 60 we got out of our fingers to be square root of 3. Type square root of 3 in your calculator. Oh, check that out. We can do this in our head and get a exact answer because we have it in radical form, or we can use our calculator and round our answer, which is why we would rather use the hand trick when possible because it's a more accurate answer other than this, unless you start recognizing this number as square root of 3, which you can if you would like to. Okay. Cotangent of pi over 12. Pi over 12 is not one of the ones I know off of my hand. It is a nice, pretty degree measurement if you were to change it. So let's leave it in radians. But I can't type in a cotangent into my calculator unless I remember it's related to what? Tangent. So really, I want to do 1 over tangent of pi over 12 in my calculator to get this evaluated number. You should get, when you do this, 3.732. Part F is a little tricky question. If you were to look at that and read it right now, what is your gut instinct to type in? Cosine. Would you what mode would you be in your calculator? You'd be in degree?
Wait, no. Oh.
Thank you for falling for my trick. It is in degrees if there is a degree sign after the number, like here, or like here. This is radians, because radians doesn't have a symbol that comes after it, which means, again, I said this last time I think, if you are meaning for the number to be in degrees, you have to show me the degree symbol. Otherwise, like this problem, this is radians. So when we want to do this, we'd make sure, first of all, our calculator is in radians, which it should be, we're just using it. And then you just type that in. Yes, it doesn't have a pi in it. That's fine. We're still measuring in radians. It's just not in exact radians in terms of pi. This would be negative 0.492. So if you want to make a big O note for yourself, that it is in radians unless you see the degree symbol. It is in radians unless you see the degree symbol. Thank you for falling for my trick. That is all part of the plan. Okay, we're able to work a little bit backwards here too. If I gave you the measurement of sine of theta, meaning like sine of theta is equal to 1/2, there's very obviously what that angle is. If I say sine of theta is equal to 1/2, what angle am I using? 30 degrees, or how many radians? Pi over 6. So we can just utilize the table backwards. Remember where that number was, either in our table or from our hand. Sine means it has to be below the number, which means this is my 30 finger. That's also pi over 6. I'm going to let you guys think through B, C, and D here. I'll give you about a little bit. C might give you some trouble, but B and D you got right now. Here we go. See if you can think backwards. Okay, at this point I feel like we either got it or we're lost. So to do tangent of theta equal to square root of 3 over 3, What is theta? 30 degrees again, which means that theta in terms of radians would be 6. Yeah. See, that's why we got it. If we just use it, we start to memorize it a little bit better. Cotangent of theta equal to 1 over square root of 3. Look, they didn't even rationalize the denominator here. That's okay, because that helps me remember that we're relating it to tangent of theta equal to the reciprocal of that. And what theta measurement do we get square root of 3 for? 60 degrees, which in radians is pi over 3. If cosine of theta is equal to square root of 2 over 2, the only way I have 2 on top is if this finger is down, which means theta is equal to what degrees? 45 degrees. And what in radians? Pi over 4. Man, we can do so much with trig. It's really, really crazy cool. The last few problems here go back to working with triangles with our trig functions. In the triangles, we're going to solve for the variable shown. This feels a little bit more like the trig we probably would have done in geometry. You always are comparing it to the angle given. So our angle given here, theta, is 34 degrees. To find the missing side, we just need to figure out what trig relationship we know. This would be called the opposite, which means this is what? The x. Hypotenuse. Which trig function uses the opposite and the hypotenuse? Sine. So I can fill out the sine version of this. If I say sine of 34 is going to be equal to the opposite value divided by the hypotenuse value. That is an equation with one variable, which means I can solve for x. To solve for x here, technically you'd multiply by x on both sides. Sine of 34x equal to 15. And then to get the x by itself, what would you divide both sides by? Sine of 34. So in our calculator, again, making sure we are in, oh look, I didn't put my degree symbol. We are in degrees mode. That's something I can type in my calculator. So first things first, make sure your calculator is in degrees, which is probably not. So change it to degrees, and then we do 15 divide by sine of 34. What is the, let's keep rounding to 3 decimals. What is the approximate value of x? 26.824. So very quickly, with not a lot of information, I'm able to solve for a lot of parts of a triangle. Let's see if we understand. Y'all got B. Figure out what we know and how it's related together to choose the right trig function. So since we know the side opposite of 57 degrees and this, well, we want the side opposite, and we know the side adjacent, opposite and adjacent are related by tangent, we can take the tangent of 57 degrees and set it equal to y over 32. What do I have to do to solve for y? Times by 32. So it would be 32 tangent of 57 degrees equal to y. Since right there my variable is already isolated, that would be all I need to type into my calculator. 32 tangent of 57 degrees. Am I in degrees? Yes, I am. Press enter. We know that y is approximately equal to 49.276 units long, however long we're measuring. Now what I want to do with this last question, because it's a big kahuna, I want to see if you can connect the dots on your own. I will help you out in a second, I promise you. But using the same idea like we did in these first two problems in A and B, I want you to find all of the parts of this triangle. A couple things I need to point out before I really just let you go. Angles are going to always be Greek letters when you're talking about their measurements. So this letter is called alpha. It's like the Greek letter A. It's called alpha. It's like a little fish. This is the Greek letter beta, like a little curly B, beta. Those are angle measurements, obviously. In geometry, when you're listing angles though, or vertices of a object, you give them capital letters. Across from each capital letter is the lowercase letter for the side. So big C is the angle, that's a 90-degree angle right here, and little c is the hypotenuse. Big A is related to angle alpha, and it's across from little a. So here, when I'm wanting you to find A, B, and C big capitals, I'm asking you for the angle measurements for each of those vertices. And when I'm asking you little a, little b, little c, I'm asking for the side lengths. So working either by yourself or with some people around you, I want to see how many parts of this triangle you can find if I give you this information. The information is that alpha is 20 degrees and little a is 12.3. With those two pieces of information, you should be able to find literally everything else, which is wild. I'm going to give you some time. Just as a quick stopping point to make sure we know what's going on. We know that this is 20 degrees. What other angle measurement do we for sure know?
70, 90.
Yeah, C is 90 degrees because it's a right angle, which means beta, or B, big B, has to be what? 70 degrees. Okay, I'm gonna let you keep finishing. Get those side lengths. We're just missing two more things now. Okay, so we know all of the things except for little b, little c. So side length B, side length C. Just because I'm gonna go in alphabetical order, I'll find side length B first. Doesn't really matter which angle you use to do this, but I'm going to continue using that 20-degree angle that we were given. How is the thing we know, this side length, and the thing we want to know, this side length, related? Tangent. So if I take the tangent of 20 degrees, it should be equal to the ratio of 12.3 over side length B. This now looks like one of the problems we did up at the top, so we can solve for B. I'm going to multiply both sides by B, and then divide both sides by tangent of 20 degrees, so that B is isolated. We throw that into our calculator, and we'd get that B is approximately 33.794. Didn't tell you how to round, so if you round differently, that's fine. It's just the notes. So there we have, bless you, side length B, 33.794. If I go back to the triangle, and again, I'm just going to stick with that angle measurement 20, and I utilize what I know versus what I want to know, how are those two things related? Sine, yes. So if we take the sine of 20 degrees, it should be equal to the ratio 12.3 divided by C. And so we're very quickly able to solve for C as well. Multiply both sides by C, divide by sine of 20 degrees, throw that into a calculator, and we'd be able to find the value C, which is approximately 35.963. So with three things, obviously one of them was the fact that it was a right angle, one more angle measurement, and one side, we can tell you everything about this triangle using Trig, which is very cool. We're going to be spending a lot of time doing this sort of stuff for different types of triangles within the next coming weeks. So the main thing you can take away from today is memorizing those things I've told you to memorize. The transition between 30, 60, and 45 into radians, as well as the trig in that table.